Aloha, Rich Alverson here. This is ITS148. And for class today, we're gonna, looks like we're into recursion. Let me share my screen. Where's my screen share thing? Share two. All right. Oh, gotta start this. Okay. All right, so here we are. This is the syllabus. And we are in today's the 15th of September. That's this one. So we're going to start recursion. I'll go through go through the challenge activities. Looks like there's 4 sections have challenge activities. And then so let's just take a peek here where we left off. Oh, I have it up here, don't I? Okay, so this is what's there now. And it looks like I've see, we've done chapter 7 and then 8. Oh, haven't done any of the labs for 8, but a lot of you have done them already. And then chapter 9, we covered chapter 9 last time. I did lab 9.5. I didn't finish lab 9.6, so I'll do that sometime. There's probably a video on it. Maybe I'll try to track that down, make it easier. Do we have video archive? Yeah, there's videos here, so I'm sure that's such a familiar problem to me. I'm sure it's in a video here. Anyway, that's if you're having trouble. You should always try to do it yourself. It's a puzzle. It's like a puzzle. You solve a puzzle. All right, so let's start chapter. The chapter on recursion, chapter 15. Do I have this up? Yes, right here. Okay, so 15, recursion. Okay, so so a function, functions can call other functions, but functions can also call itself. And a function that can call itself is called a recursive function. And it's not as confusing as it first sounds. You just have to make sure that the function that can call itself has to be clear when the recursion stops, or when the function will stop calling itself. Okay. And so here's an example of a recursive function, and we're calling it countdown. And here's the so whatever we start countdown. In this case, the argument to start countdown is 2. That's what count is. And you notice each time we call it, we are subtracting 1 from it. So the first time we call it, it looks like it's 2, but then the next time, this is when it calls itself. It calls itself with what it is with the count 1 less than that. And then here we see this is the terminating condition. This is when the recursion stops. When count gets all the way down to 0, it's not going to call itself again. It's just going to print out go, and then it's going to be done. Well, once it's done, then all of the rest of them are done as these functions return from doing what they're supposed to do. And so we see then that this is going to print 2, 1, go, because the first time it comes in, it's going to print 2, and then it's going to call itself again, and it's going to print 1, then it's going to call itself again and count as 0, so then it's going to print go, and then it's done. And so that's all right. So make sure you do these to make sure you understand how these work. If it looks like, how many times will countdown be called if the script calls count 5? Well, this one, it looks like it called it 3 times, and it was 2, stops at 0. So it looks like it is 0, 1, 2. This must be 0, 1, 2, 3, 4, 5. So maybe the answer is 6. Looks like it is. All right, so make sure you understand that. Oh, here's a challenge. Calling a recursive function. Write a statement that calls the recursive function. I better pay attention here. Yeah, I gotta fix my Okay. Oh, yeah, okay. So it was a personal message to me, so I'll display that on the screen here. Right? So write a statement that calls the recursive function called backwards underscore of alphabet with an input starting letter. With input called starting letter. Okay, so we have an input called starting letter. Here it is. And then we're supposed to write a function that's going to print out the alphabet backwards. And so it's going to start at a starting letter, and then it's going to call this thing. I guess that's what it does. So I'm going to call it. I didn't do this beforehand. So I'm going to put that in here. I'm going to paste it there. But I'm going to does it look like this up here? Yeah, it does. I'm going to change this to starting letter. Copy, paste, and don't put that there. So what's going to happen is, let's say we put in F. And then it's going to call it, and it's going to come in here. And is it A? No, it's not. It's F. So then it's going to print F, and then it's going to decrement F to E. That's what this does here. See, this takes F, figures out what the ordinal value of F is, and that's going to be a number. It's the ASCII number. It's called the ASCII number. And F, I don't know what it is. It's 91 or 95 or something. And then it's going to subtract 1 from it, and all of the letters are in order. So it's going to, so basically we're changing it to the ordinal value of E. And then we take that ordinal value and we turn it back into a character, and that's what the CHR function does. So that's how the decrement works. And so then it calls it, and lo and behold, I think this is all we need to do. A does get printed. So let's see if this is right. Oh yes, well, gee, that was difficult. Now, some of these early recursive algorithm examples are kind of dumb. You wouldn't normally write the solution to these simple problems using recursion, but they're just good to illustrate to get you used to it. And then there are some algorithms where it's just much easier, much better to express them recursively than iteratively. You can always take a recursive algorithm and convert it to an iterative algorithm with a loop. All right. An algorithm is there a challenge? No, there's not a challenge. There's not a challenge here, but this talks about a recursive search algorithm. Mow the lawn, mow the front yard. Okay, so recursive search. Oh, I see. Binary search. Right. Okay. So you know the way a binary search algorithm works is, first of all, it assumes that the list is in order. It's in order, and so it assumes that the list is in order, and it assumes that you can index any element in the list with equal computational speed or computational complexity to any other one. So you can randomly access any element, same amount of time to access any element. So then what you can do is you can first take a look at the middle element and see if what you're looking for is higher than the middle element or lower than the middle element. And in this case, what we're looking for is going to be lower than the middle element. Okay, so that means now we just need to look at this bottom half here. Now, what we've done is in one search, we've eliminated half of them. we eliminated 50, possible, tests by just that one, and that's because it's, we're taking advantage of the fact that it's in order. That's the main thing. So then we go and we cut that one in half, and is our number lower or higher than 25? And the answer is it's higher. So now we've eliminated half again. And so here you see we keep eliminating half and half and half until we find it. Now let's see, a recursive find carrying out a binary search algorithm. So the recursive, the way you would look at this recursively is you pass the algorithm the endpoints, the endpoints, the beginning point and the end point of the set of elements that you're going to examine that are in order. And what the algorithm does is it cuts it, and it looks at the middle element, sees if the middle element is the one that they're looking for. If it's not, it's going to be below it or above it. And so then what it does is it calls itself again on the half that it figured out that it was in. So each one of these is calling itself. It's calling itself. So this is a recursive algorithm. And so you can go through this to figure out, to make sure to see how that's expressed algorithmically. Yeah, shoots. I owe you. I have to set up for you to do the assignments. I've got to set up these servers for you. And in fact, I have time this afternoon. I'll do that. And then it takes a couple days for the secure servers to get all lined up. But let's see. I'm talking about these here. And several of you have contacted me saying, "Oh, it doesn't work, and it's because it's not up yet." But I promise we'll do that this afternoon. It doesn't take me very long, but I do need to wait until the class, the enrollment is settled, and there's people still dropping. There's not people adding anymore, but anyway. So because I run them all at once, I run a script, sets them up. Anyway, so make sure you understand that. And adding output statements for debug. Okay, this is an important thing to look at. It's hard to debug. Sometimes it's hard to debug a recursive algorithm because you kind of don't know where you are. And a common debugging technique, which you've probably learned by now, is to throw in print statements. You're wondering what something is at a certain point in your code. You think it's equal to a particular value. You just throw in a print statement and it prints out. Oh yeah, you either confirm it or you say, oh geez, that's not right. And of course the way you do that with recursive, the way you do tests like that when you're dealing with recursive functions is you can pass this indent value, this indent variable, this indent argument, which is simply the number of spaces to indent the print statements. So each time you're testing and checking out if some value is what you think it is, first of all, you print the indent. And each time you call the recursive function again, you add like 3 spaces to the indent. So the deeper recursion you go, this indent is going to get bigger, more spaces. And so here we see this print statement is 1, 2, 3 recursive calls in. This one's only 2 recursive calls in. This is 1 and so you see, so it's easier to see how these values change as the recursion goes deeper and deeper. So that's what this is. All right. Creating a recursive function. you know, I don't know if you're going to ever come and decide that, gee, this is a great function. I should write this recursively. But I guess if you're traversing through like a directory structure, if you're looking through, if you're looking for a file in some directory structure, I guess a recursive algorithm may help. But that's just going to be a recursive, you know, binary search tree algorithm. So you're gonna by the end of this class, you're gonna learn all of the times. You're gonna learn the examples of algorithms that, for all the times that you're going to want to use a recursive function, it's probably going to be one of the algorithms that you learn. I think it's, if not, you're going to learn some of them in this class, and then you're going to learn the rest of them in ITS148 if you ever take that. All right, so see if we go back here. Binary search trees. You know, that would be, I'm looking for a particular file with a certain file name, and I can't remember what directory it's stored in, and you have this, you know, you're on your computer, and you know, this algorithm is what you use, and it's, you know, we learn it here and so on. All right, so let's go back to what we're doing. So we are doing creating a recursive function. All right, so when we create a recursive function, and I'm not really that great at this. I mean, I don't write a lot of recursive functions, but you have to write the base case, and that's the case that returns a value without performing the recursive call. And so you usually put that at the very beginning, because, you know, that's so you know that it's there. If it's not there, if you should mess up, it's the same as having a while loop that never terminates. But a while loop that never terminates just sits there and uses up processing time, and nothing works on your computer until finally the operating system goes, hey, this process has been taking too long. It must be in a tight loop. So the operating system terminates the job. For the recursive function, if you don't have this base case correctly, then it keeps calling itself. And calling a function uses up memory, okay, because it has to set aside a new set of variable space, because the function is called again. The function calls itself again, and there's local variables, then they have to be created again. And so they're created on what's called the stack. And so if you get into a case where you're calling a recursive function keeps calling itself, it's not going to run out of time. It's not going to take too much processing time. It's going to run out of space. So the operating system goes, whoa, what is this process? Why does it need 1,000 times more space? That must be a recursive function that doesn't have the base case correct. So anyway, that's just to the difference. But you know, you can solve any recursive function iteratively, and you can and many iterative functions you can solve recursively. The recursion doesn't really add any new power, just makes it easier to in some cases it's just easier to express the problem as a recursive function. All right, so you come up with a base case and then the recursive case, and the recursive case is where it's going to call itself again. Here's a factorial, and it's recursive, writing a recursive function for factorial. First you write the base case, and then you add the recursive case. So the base case is you know, it's coming down, it's, you know, you call it, where is it, where do you call it? Anyway, you call it with a number saying what's the something factorial, and to compute a factorial you take, you know, it's n times n minus n times n minus 1 times n minus 1 times, you know, or times n minus 1 times n minus 2 times n minus 3 all the way down to 1. 2 actually. And so this is a nice function you can express recursively, because factorial is equal to the number that you called it with times times the factorial of the number just below it. You know, so see, so if it's 5, so let's say you call it with 5, then 5 factorial is 5 times 4 factorial, right? Because 4 factorial takes care of 4 times 3 times 2 times 1, and then you multiply that by the 5, and then you have the 5 times 4 times 3 times 2 times 1. So there, you know, that's it. Now you have the recursive case where we have it calling itself, and then we have the base case where if it comes down to equaling either 1 or 0, then it just returns 1. Then the value is 1. Then this is going to be so 1 factorial is 1, and 0 factorial is 1. So that's why this can just return the value 1. All right. So anyway, times. All right. Here's a challenge activity. Add an if branch to complete the double pennies base case. Okay. Write down. I don't want to steer you wrong here. Shooting. I think you know, I think recursion is sort of intellectually stimulating and all that, but it's you know, whenever I teach it, I gotta get my mind around it again and make sure I try real hard not to confuse you. I shouldn't talk so much because these textbooks are really good at explaining stuff with all the animations and so on. All right, so I'm supposed to write the base case, and so what this does is, oh, I see. If you double the number, if you double your double your pennies each day, then after 10 days you have, you know, that's 2 to the 10th power 10. You have a lot of pennies. 2 to the 10th, 1,000 pennies. If you start out with 1 penny and you double it, the number of pennies you have every day. In 10 days, you'll have 1,000 pennies. Okay, you'll have $10 and 24 cents. So if the submitted code has it'll stop running after a few seconds. Yeah, see, so this is what happens. It'll stop running after a few seconds because you run out of space. Does not print. Okay, so right. All right, so first we're going to read the starting with this number of pennies, and then these are the number of days, and so we have double pennies, and so we're going to start, and it's going to be user days, and each time we call this, okay, so we're going to be calling itself, and each time we call itself, we're going to double the number of pennies, but we're going to subtract 1 from the number of days. Okay, so this is what makes it go down. Each time it's called, this goes down, and probably if it starts at 10 days, we decrement down to 0, so that'll be the 10 days. And so this is going to be something like if num days is equal to 0, it could be less than it's got. Then we just say that we're done, and the total pennies. Yeah, we return total pennies. We're done looping equals whatever num pennies is coming on. Right? So I think this is the answer. Very good. All right, write the recursive case. Okay, so write the code to complete the factorial str's recursive case. Okay, so boy, these are tricky. All right, so we're going to start out here. We're going to read in a number. Oh, we're doing, is this factorial? Okay. Right. Oh, is that what it's supposed to print out? Okay. So we read in a number, and then we write out the number, and then we write this, and we write that out. So that's this. That looks like it's this being written out all the way to there. And then we call factorial string on the value that we started with, namely 5. And the value again. Okay, because it's a 5 times, well. All right, so it comes in factorial counter. This is the counter, and this is the value itself. Okay, so this one is going to end up increasing. And this is just going to be decremented each time. The first one will be decremented each time, I think. Okay, so yes, right. If it's 0, then you want to just add a 1 to the output string because you're at the end. Otherwise, if the factorial counter is 1, then you want to write string counter. Okay, so what we're doing is we're writing this. And this is this part. So that takes care of those two parts, and we're supposed to write our code here. Okay. So when the factorial counter is 2 or higher, then we need to add whatever the factorial counter is, and that's going to be this thing. Add that followed by an asterisk. So it's like we're doing this. The first time it comes in, it's going to add that to the string. And then we're going to increment the counter, or we're going to decrement the counter. The next counter is 4. And then the next value is the next counter times fact value. Where's that? So it's coming in. Got it. Okay. All right, and so this would be something like it's factorial string because we're calling itself factorial string. And it's going to be next counter, because it's the fact. That's this coming in, and here's where it's decremented, and so that's what we want to send on. And then this just has to be the number that we're computing, because each time it's called, we multiply that by the next counter. So this is just next. I guess. I commend those of you that have done these already. All right, recursive math. Okay, recursive functions can be used to solve certain math problems, such as the Fibonacci sequence. The Fibonacci sequence is you know, it's like starts at 0 and 1. Okay, and then this number is the sum of the last two numbers. So this number is 1 plus 0, it's 1. This number is the sum of the last two numbers. Well, the last two numbers are 1 plus 1, so that's 2. This number is the sum of the last two numbers. You see it's 1, and this number is the sum of the last two. The sum of the last two, all the way up. Okay, that's the Fibonacci sequence. It goes on forever. So the pattern is to compute the next number by adding the previous two numbers. Starts with 0 and 1. So you know, this is where, okay, so how many steps would you like? And so we're sending it the first number, 0 and 1. These are like the two numbers to add, and it prints it out. And then if the run count, which is this thing, this is going to be the thing that terminates. This knows each time it increments. Okay, so here, this is how many times you want to do it. 10 times, you know, 20 times, whatever. How many times you want to do it. And so then we call it, and each time we call yourself, we decrement that run count. And when it gets down to 0, 1, gets down to 1, then it's gonna not do anything and return. And then they're just gonna start returning. I guess that's what this does. Okay, so oh, you can use it for, are there any, this is 15. Oh, recursive exploration of all possibilities is next. Oh, this is the math function. Okay, greatest common divisor, very famous algorithm, because it's used to create public keys, RSA cipher public keys. And basically it's finding the greatest common divisor between two numbers. And if the greatest common divisor is 1, if there's nothing that divides any of them evenly, then those two numbers are considered relatively prime, and then you can multiply them together, and that can be the secret key and all that. Anyway, so here we want to find the greatest common divisor between two numbers. So we read in the two numbers, and we can't have any number below 1. It's got to be positive numbers, and then you just call the greatest common divisor, and it comes in, and if the first one mod the second one is 0, then that means that this is a common factor. It's like if you have some number that's bigger than some number that's bigger than n2 divided by n2, and if the result is 0, then you know that n2 goes into n1 evenly. You know, it's kind of like if you have, you know, 45 divided by 5 is going to be, the mod of that is going to be 0. It's going to be 9 remainder 0. So that's because why? Because 5 goes into 45 an even number of times. So that's the terminating condition. Otherwise, you call greatest common divisor again on what that mod value was. So if it's like, you know, and so this number keeps on getting smaller, and so that means this number keeps on getting smaller, and this number keeps on getting smaller. Eventually you'll get down to where the n2 is the greatest common factor, and it could be it, and it might end up being 1. All right, so So that's another recursive algorithm, and you can make sure you understand it. All right, so write code to complete raised to the power. For example, this example is for practicing recursion. A non-recursive function or using a built-in function would be more common, of course. But okay, so the function is raised to a power, and so we read in a base and we read in an exponent. So in other words, we're going to take the base and we're going to multiply it by itself this many times. And so so we can just use a really? Okay, let me just check this. I want to make sure that this is. Oh yeah, okay, got it, right. So this number is going to decrement down to 0, and each time it's decremented, you multiply this by that number, and that will multiply. You know, this is 4 times 4. If this were 7, 4 to the 7th power would be 4 times 4 times 4 times 4 times 4 times 4 times 4. So this is going to be the loop thing. So that's why it's the exponent. This is the base. So we are raising the base to the exponent, and so what we're going to do is each time we come into this, we're going to take that base value and multiply it oh, okay, yeah. So we'll just take it and raise to power of the base value to the exponent value -1. So so each time so it's kind of like we start out with this. So let's say it's 5. Let's say it's 4 to the. Let's do something better. Let's say it's 5 to the 3rd power. So that'd be 5 times 5 is 25. Times 5 is 125. So that would be like 5 times 5 times 5 to the 2nd power, and that would be that comes in here, and then this ends up being times 5 to the 1st power. Anyway, no, I see that's not quite right. But anyway, this is the answer. I didn't explain that right. Oh, it's not the answer. Okay. Oh, got to put a 1 there. So each time this is called, it gets decremented by 1, and you multiply by the base value again. So it multiplies it by the base value, the number of this user exponent number of times. All right, so anyway, this is probably the answer. Okay, so here we are. This is a good algorithm to express recursively. So it's a okay, so what are we trying to do in this problem? Oh, this is an all possibilities framework. Okay, so recursion is a powerful tool for exploring all possibilities, such as all possible reorderings of words, letters, all possible subsets of items, all possible paths between cities, and so on. And so here, consider the printing all possible combinations of words, letters. We start with A, B, C. The first one, let me see what this does. These possibilities are obtained by thinking of three choices. First, you choose the first letter. Is this the chooses the last letter? The first letter can be, if the first letter is A, okay, A, B, A, C. You know, I'm going to have you go through this. Why don't you go through this? I'm just wasting our time here. There is a I know there's a problem that does this. Is this, you know, all permutations of names? Okay, well, maybe we'll get through this at that time. This is find the distance of traveling to 3 cities. So this way you can find the shortest path between the shortest path to visit all 3 cities. All right, what is this one? Enter the output of recursive exploration. Oh, good. This should be a good one to help us understand what's going on here. Okay, so let's just 987. 8778 9779. Okay. All right, I'm just going to start. So we come in here, we have a list of numbers to scramble, and we have a list of the results, and we're gonna the numbers to scramble are 1, 6, and 3, and then we're gonna scramble the 1, 6, and 3 and we're going to put the result in this list, in this empty list. And where do we print? Here's where we print. Okay, so we come in here and we have the numbers, the remaining numbers described. So each time we do this, we're gonna take a number out, and then we're gonna add it to this. So so if the length of the remaining numbers is 0, that means we've already created all of the possible. We finished creating a list, and it's going to be a three 3-digit list. Then we print it out, because we've got in here we've got 0, 1, and 2. But the first time we come in, this, which is this, is empty. So it looks like okay. So and then so each time we come in, something's going to be added to this, and the number is going to be, and this is going to be decremented by it, and it's going to be taken out of this. Okay. All right. So for 1 in the range of the number of the remaining numbers, so the first time it comes in, it's going to be 3 as 0, 1, and 2. Temporary remain numbers. Oh, we're just going to make a copy of it. That's a copy of it. And then we're going to take the first number, which is going to be 1. And that's this. So this is just a number. And this is going to pop off the element off of here. I wonder why we just didn't pop it off anyway. Okay. And then we're going to append it onto, we're going to append that remove number onto the scram nums. And then we're going to, so the first time we go in, we're going to, this is taking a long time, isn't it? So the first time we're going, it's going to be a 1, because that's the first one we're pulling off. And yeah, so the first, so that's the 0th one. And we append the 1, and then we scram nums. Oh, I see. Okay, and so this is the recursive call. We call with the remaining numbers because we popped off. So we popped off the 1, and what's left is the remaining ones. So 1 is gone. So what's back here is the 6 and the 3, and this has a 1 in it. And so this is a 6 and a 3, and this has a 1 in it. And so then we're going to go from 1 to 2. I see. This was where we put the. So it's going to be 1, 6, 3. 1, 6, 3, and the next one is going to be 1, 3, 6. And then I think we start with the 6. I see, that's why I put that in temporary. So then I think it's 6, 1, 3, and 6, 3, 1. And the last one I think is 3, 1, 6, and 3, 6, 1. Okay, that's what I think it is. What did I get? Oh, where is the last print? This is this, it's that separate. Where's the last print? I don't see the last. Oh, this is just separating. Oh, no.
It's that pesky return.
Huh? Yeah. Oh yeah. Oh, what was that again?
Is it that there's no return after 361?
Right. Yeah. That's the answer. But I'm trying to figure out how the code said that. Well, this separates. Well, anyway, yeah, I guess it's supposed to be like that. But I'm not following. Maybe I'm confusing. That's a print, but separator is. Oh, okay. Never mind. I was confusing. I was thinking that was the end, but no, that's separator. That's just a separator. So yeah, each time it's going to separate, and this means so this is how you make it so when you're printing it out like this, it doesn't put a space in between. It puts nothing in between. Anyway, so that's why I was confused. I was thinking that this was an end, but of course that doesn't make sense either. Anyway, okay, so you can do the next one, I guess. All right, so let's do, should we try a lab? It's 2:20. This class goes till 3, no, it goes to 2:45, right? Yeah, okay. Yeah, let's try one of these labs. Why not? So this is recursion, and yeah, right. Most you haven't done the labs. All right, we might as well try this one. Okay, I'll put a linked list. I don't want to. Okay, write a recursive function called print list that outputs the integer value of each node in a linked list. Function print list has one parameter, the head node of the list. The main program reads the list of the linked list, followed by the values in the list. Main program first reads the size of the list, and then it reads up the list. Okay, so wow, I gotta write all, oh, there it is. Okay. I'll write print list. Okay, so what we're doing is we're writing okay, we're writing def print list. And this is a node that we're printing. These are nodes. Yeah, okay. Okay, was there another? All right, so we have these nodes, and a node consists of a value plus a pointer or the address of the next node. So when you initialize it, there is no next node. If you insert a node, after, where is this one called? Let's see, let me just go down here. You read in the size, you read in the value of the that's why you assume it has at least one. Assume it has at least one. Okay, so you read in how many there are, and then you read in the first one because you know there's going to be at least one, and you set the head node. You create it's a node type. It's create a new instance of a node. Create an instance of a node with this value, and that's what this is going to be. This is a node, and then this is the last node is going to be the address of the head node, because there's only one node in this list now. And then we're going to loop for n more, for size minus 1 more times. That's why we're starting at 1 instead of 0. So we're going to loop size minus 1 times. Each time we're going to read in a new value, create a new node from it, and insert the node after the last node. So we're going to be inserting them on the end each time. And so, and we're going to update this node pointer to point to the last node each time. Normally, we don't do stuff like this in Python this way because Python's got, it's got the list data type that's got a whole bunch of methods to help us do this. But if you're doing this in any other language, this is how you'd have to do it. So, and all of these textbooks were sort of converted from, I think Java may have been the first one, and then they convert these other textbooks from that. So anyway, so this prints that, and we're supposed to write method that does this. Okay, so first, I guess we got to check if the node is empty, then we're not going to print anything. So first, let's test to see if node. We have to make sure the node is not equal to none. It's empty node. It's a keyword, none. And if it is equal to none, then we can we should do this. Call this one. Print data of the node, and then we want to call print list on the next node. And so print list is going to keep on calling itself, just printing the node that it was called at, and then calling print list again on the next node, and it's going to keep on going until the last node is the last node. The last node is not going to address a new node. This is not going to be a value. This is going to be next node is going to equal to 1. See, the first one, whenever we make a new node, which is here, whenever we make a new node, the next node value is none. And then this thing takes the new node and we stick it onto the last node. And last node is now pointing to this node, but then this next node value will be none. So the last node that was created is going to have that value of none. And so when we're printing the list, it's going to keep calling itself until this is false. And when this is false, it's just going to return. We have to finish this first. So once we print the node, then we're going to call print list again on itself, but not on itself on the next node. That's, we're going to use this method here. So we should say node dot get next. So print list, operates on a list. It operates on a list, and it starts with the head node of the list, and then it prints all the nodes in the list. And the way it prints all the nodes in the list is it starts by looking at the first node, prints that one, and then sees there's another list, that this thing is hooked onto. So then it just calls print list on the next one. And so each time print list is called, it just ends up printing one node, and it calls it. It ends up being called as many times as there are nodes, like +1, because it's going to call it on the last one. The last node, this value here is going to be none. It's going to return none. And so when this comes in, this is going to be none. So then it's going to stop, and then this is just going to return without doing anything, and then everything returns after that, because they're all going to return from this, which is nothing after that. So it just returns. And I think this might be all. Let's see if this. Do I have to put any data in here? Okay, I'll put this data in here. Print data is not defined. What should it have been? It should be. Oh, I did something wrong. Do I gotta put something? Oh. Print data is a method of the node. So it's a method of this node. So I gotta say that I gotta address it this way. Just like I did that. All right, print data takes one positional argument, but two were given. Okay, it takes one positional argument and two were given. One print list or print data. All right, where did so I gave it two, huh? What did this is on line 20 in print list. Oh, no, okay. 20 in print list. I don't think I, oh, I don't do this, do I? Right, what? Okay, yeah, there's no parameter. This is not a parameter. There's no parameter, so what am I doing here? That's how you print the data. Okay, so this looks like the right answer for this. So I'm pretty sure if you submit that, you'll get the points. Let's do we've got some time here. Let's do this next one. All permutations of names. Okay, so, you know, this is just going to be the same as what we did before. It's going to be the same as the one that the challenge that we did, right? So we're supposed to write that method. Well, let's see. I'm going to go back and look at, I think that was it this one? Why is it making me sign in again? Oh, I'm in the wrong. Oh, wait a minute, this is messed up. This should be 148. Here's 148. Okay, I wanted to look at I wanted to look at all the possibilities. I'm doing all the possibilities. So is this one? Oh, this one here. All right. I'm going to separate this out. Put it over here. All right. So we do it the same way, except for we use different methods and stuff. All permutations of names. First of all, we're going to see, we're going to check the size. So this is the input. And so it's going to output this. So you notice it does the same thing. Julia, Lucas, Mia, and then it does Lucas, Mia, Mia, Lucas, and then Julia, Mia, and Mia, Julia. And for Mia, it does Julia, Lucas, and Lucas, Julia. That's what the output looks like. So the first thing we're going to do is, I suppose, we're going to figure out what the size of this name. Okay, name list is the here we're building we print. Okay, so name list is going to be this thing. And perm list is going to be, I think it's this thing. And so first we read it up. We read it up and then we split it on the space, and that gets equal to is what's thrown in there. No, this must be the opposite. Permanent list. I think that this must be it's like this over here. Here we're appending onto num scramble name. So name list is like num scramble, and here name list is like num scramble, and over here num scramble is the first one, and over here name list is the second. So they're flipped. So this means that this list is going to be stuck in there, and this list is going to be this list. All right, so what we're going to do is, first of all, we want to see what the size of name list is. Name list is the list of names that we're using. And yeah, right. And then we're gonna okay, if size is equal to 0, that's this case. If size is equal to 0, then we're gonna do this. We're gonna print it out. And how do we print it out? Well, I guess we do this. For I in range of the length of the permanent list. This is the list that's built up. We want to, if okay, if I is equal to the last one, if I is equal to the last one, which is this, if I is equal to that, then, well, I'm sorry, this is too confusing for me. If I is less than that, if I, before I reaches the last one, I want to print out the you know, whatever the entry is, and that would be whatever perm list of I is, followed by a comp. No, I'm not printing out. Yeah. Yes, I'm here. This is going to be. What is perm? Oh. Well, I guess I'm confused, but here we print the perm list followed by n equals So this looks like we're just printing one. Oh, you know, this perm list. All right, well, I'm just going to continue this. I'm not sure I have this right, but so it does that. Otherwise, if it is the last one, then print the last one without the comma and with the carriage return. So this thing prints out, I guess, a finished one of these. If size is not equal to 0, in other words, if we still have some names left to append onto the permanent list, then we are here. Else, the size of name list is not equal to 0. It's bigger than 0. For I in the range of whatever the size is, it has to append those onto perm list. So we need to make a copy. And let's call it new perms equals perm list. A copy of it. And then we're going to append. So this is name list. These are the rest of the names. Let's say let's say we've got Julia on perm list, and let's say that name list still contains Lucas and Mia. Name list still contains Lucas and Mia, and so this is going to go range from 1 to 2. So first it's going to make a copy, and then it's going to append onto this new perms equals and name list. Then new names. So this is kind of confusing. New names. I'm just typing in the code here. You guys can figure out how it works. New names, name list copy, and then you want to pop it off. Pop. Pop off that particular one, and then you want to call itself again. And it's going to be on the new perms list, followed by, and then the new names list. So new names is what it's pulling it off of, and it's going to add it up. It's going to be adding names to perm list when it comes in here. This is going to be, so the next time it calls itself, new perms comes in as perm lists. And where do we, oh yeah, I see. And this pulls off a copy of it. Yes, I see. So it comes in, and let's say this is the perm list. So then as it goes through this loop down here, it's going to go, size is equal to 2. It's going to make one that looks like this, and it's going to make another one that looks like this. And it just gets printed out. It gets printed out here. When it comes in and size is equal to 0, that means it's done. It's got all the names in it in whatever order it is, and this thing just prints it out, and that's it. So I'm going to try this. We're at the end, so I'm going to try this. And what am I supposed to put here? This yeah, that looks pretty good. All right, I think that's the right answer. So it's the end of the period. So I will continue this next time. All right.
Thank you, Professor. Appreciate it.
Okay.
Thank you, sir.
Yeah.